Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Today we're working out of Elementary Principles of Chemical Processes, 3rd edition. We're doing problem number 3.21, and I'll read the problem statement. Things were going smoothly at the Brow Bridge Drug Company pilot plant during the midnight to 8 a.m. shift until Therese Lagnappe, the reactor operator, let the run instruction sheet get too close to the Coleman stove that was being used to heat water to prepare Lagnappe's bi-hourly cup of community coffee. What followed ended in a total loss of the run sheet, the coffee, and a substantial portion of the novel Lagnappe was writing. This kind of reminds me of The Importance of Being Earnest. Anyway, I'll go ahead and read the second part of this problem that's actually pertinent to the math. Okay, remembering the less than enthusiastic reaction she got last time she telephoned her superior in the middle of the night, Lagnappe decided to rely on her memory of the required flow rate settings. The two liquids being fed to a stirred tank reactor were circulosic acid, CSA, molecular weight equals 75, specific gravity equals 0.9, and flubitol, FB, molecular weight equals 90, specific gravity equals 0.75. The product from the system was a popular over-the-counter drug that simultaneously cures high blood pressure and clumsiness. The molar ratio of the two feed streams had to be between 1.05 and 1.1 moles of CSA to moles of FB to keep the contents of the reactor from forming a solid plug. At the time of the accident, the flow rate of CSA was 45.8 liters per minute. Lagnappe set the flow of flubitol to the value she thought had been in the run sheet, 55.2 liters per minute. Was she right? If not, how would she have been likely to learn of her mistake? Note, the reactor was stainless steel, so she could not see the contents. Okay, so let's get started here. Start writing down what we've got. Okay, 3.21. So first off, we've got, let's draw a picture. We've got a stirred tank reactor. We don't know if it's totally closed or if it's open at the top. They say it's stainless steel, so you can't see into it, but we don't know if there's like a ladder on the side here where you can kind of climb the ladder and then look up into the tank, or if it's a totally closed reactor that would be sealed and then it has like a pressure gauge on it or something like that. Yeah, so let's go ahead and write down what we know. We know that we've got a certain amount of FB going in and a certain amount of CSA going in. We know that CSA has a molecular weight that equals 75. I'll just do grams per mole. And then we know that CSA specific gravity equals 0.9. FB molecular weight equals 90, and specific gravity equals 0.75. Okay, what else do we know? We know that the flow rate of CSA, we know this flow rate, so this is volumetric flow rate, equals 45.8 liters per minute. Okay, and that's the only thing, I think those are the only things we know. Oh, and we know that she set the flow rate of FB at 55.2 because that's what she thought the flow rate should be. So this is the one we know was running, but this is the one that she set afterward. And then we're trying to figure out if this is the right flow rate she should have been running. Okay, so the criteria that we have to meet is that CSA moles of CSA over moles of FB has to be between these ratios. Okay, so let's figure that out. What we need to do is figure out how many moles we have here in this stream going in, and then we need to figure out the range. We need to figure out this range and find out where this flow rate falls. Okay, so let's start here so that we can know what the ratio should be. Okay, so we've got 45.8 liters per minute, and that's liters of CSA. Okay, then we're converting this into moles of CSA, so we need to use the specific gravity here. Use 0.75 grams per milliliter, 10 to the 3 milliliters per liter. So now we're in grams per minute, and we need to turn it into moles. Oops, had the wrong thing there. We're in CSA, so 0.9, there we go. And now we're in 75 grams per mole. 75 grams per mole. Okay, so now we have moles of CSA. 550 moles per minute. Okay, CSA. Now this molar ratio, moles of FB, we need to figure out to find out the range that we're allowed to be in. So if we had 550 moles per minute of CSA, that means FB could only be, okay, so the moles of FB can only be between these values, 523, or 520, and 500. So our moles of FB need to be between these values. And I've calculated what that was based on this and this. Okay? So now we need to find out what she actually set it at right here. So let's convert that into a molar flow rate. First, let me put the units here. This is in moles per minute. Okay. So she set it at 55.2 liters per minute. FB has specific gravity of 75 and molar mass of 90. Okay. Okay, so this is the flow rate that she set it at. So she set the flow rate too low. She needed more flow rate. So there's too much CSA going into the reactor compared to how much FB was going in. So she was not right. She was not correct. She was not in this range that we calculated. Okay? If she was not right, how would she have been likely to learn of her mistake? Okay, so let's take a look at our reactor. We've got a certain amount of stuff going in, and you have to have a certain product going out. And this, the volumetric, or not the volumetric necessarily, but at least the mass flow rate needs to be the combined mass flow rate. Okay, CSA, there we go. It needs to be the combined mass flow rate, and if the reactor has less mass going out than it has going in, then let's say you have a fluid level in here and the tank is open. Okay, so if the tank is open and you have a fluid level in here and you have more mass going in than you have coming out, then this fluid level is going to rise. And that is the case. What would happen is that if you have the ratios off, it said the reactor would form a solid plug. So this solid plug might get so full that it blocks the mass flow rate coming out. So the mass flow rate would reduce coming out, and so you would start having a rising level in the tank. Now, if the tank was open, this fluid level would get so high that it would either get into, maybe you've got a safety valve or a safety pipe or a skimmer or something right here in the tank, and this would lead to a pipe that goes to like a pond or an overflow or a spill or something like that, and you would start overflowing the tank and it would go into the spillway. So you would start losing a lot of product going into the spillway instead of being in the reactor. If there was no spillway, it could just overflow the tank and then just spill onto the floor of the space here, and then where does it go from there? It's just on the floor of your factory, maybe. So that would be bad. The other thing that could happen is, let's say this tank is totally closed and the tank is pressurized. Okay, so this is a kind of a dangerous situation where tank is pressurized. You've got let's say you've got like a pressure gauge right here. Well, you start pressurizing the contents in this reactor. So if you did have like a gas, if you did have like a gas or something in this space right here, you would start pressurizing this gas, and then the pressure of that gas would build and build and build until you have so much pressure in there that either the tank fails or your pump fails, or something happens where you back something up in these inlet lines and something bad happens. Your tank could rupture, your seals or your pipes or things could explode. You explode a rupture, or you have like little pressure relief valves or something on these lines, and those start whistling or going off. So lots of different things could happen depending on the design. That's how she would likely have figured out her mistake. So one of these indicators, one of these pressures would start going off, or she would start seeing the tank level rise, or she would, if she was particularly unattentive, she would just start spilling stuff onto the factory floor, or it would start all the reagents would start spilling into a spillway or something like that. So anyway, great. If you guys think of any other things that could have happened, just put it into the comments, or something like that. Start a conversation about that. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insight or a question you may have. Also, if you found any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.